Okay, today we are going to be discussing lesson 3.1, the derivative of a function. We've already looked at derivatives of a function, we just haven't really called them that. The derivative of a function is simply the slope of that function, the instantaneous rate of change. So we can use our limit formula. The slope equals that limit as h approaches 0 of f of x plus h minus f of x over h. Just like we've done that in the past, if we put in x plus h instead of a value, 2 plus h or 3 plus h or whatever, we'll get a formula that will give us the slope at any point on the graph of f of x. When we do that, we have found the derivative formula. Now to find the derivative at a point, we simply take the limit as x approaches a. So we're going to let a be some number. And we're going to have x stay as a variable. A is going to be a number. And if we do that, and we put our function in here and monkey it around until we don't have x minus 0, or we don't have x minus a equals 0 in the denominator, we can find the slope at any point. So this formula gives us a point, slope at a point. This will give us a formula for slope. Or, of course, if we put in one value here, we could get a point out of that too. Now, when we talk about derivative, we're simply saying derivative is just another way of saying slope. And if it's a whole function, a slope function, that's telling us the rate of change of the slope at every point of f. And that is instantaneous rate of change. Change is a big deal in our world, so we need to study it. Now, notations for derivative. Well, lots of ways to say derivative or slope or instantaneous rate of change. We can go with y prime. We could have gone with f prime, which is just read f prime. We might say dy dx, or the change in y over the change of x, or the derivative of y with respect to x. Three ways to read that. If you see df dx, that's the derivative of f at x. And if you see d dx of f of x, that's the derivative of f with respect to x. They all basically mean the same thing. You just say them a little differently as you read them. We will see this y prime, f prime, and dy dx very often, and we want to be well-versed in how to use them. Now let's look at finding a formula for the derivative. We're going to look at an example. We're going to find a formula for the derivative of f of x equals x squared. Well, the first thing we'll do is we'll write our derivative formula. So we'll write that definition of derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. And now we're going to have to plug this formula, x squared, in here, which is going to give us x plus h quantity squared, because that's our input, minus x squared, because there's our input here. When you expand that, you have x squared plus 2xh plus h squared minus x squared, and these are going to nicely cancel out. We still have h in the denominator, so we cannot replace it with 0, but I see we could factor out an h from each term. So we'll do that, and once we've done that, now we have the limit as h approaches 0 of 2x plus h. Well, now if I put in a 0 here, I just have 2x. So right there, f prime of x equals 2x. That is our derivative function. F prime of x equals 2x when f of x equals x squared. So we can write that. If f of x equals x squared, then f prime of x equals 2x. And that's going to be the derivative that you put any point in here, and that will give you the slope of this function at any point on the graph. Now, if we want to look at our derivative, our alternate definition, that would be finding the derivative at a point. All we have to do then is we're going to use this definition, f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. If the limit exists, remember there's places it doesn't exist, corners, cusps, jumps. We won't find a limit there, obviously. Now, we're going to look at this, and we're going to find f prime of 2 when f of x equals x squared. So basically, we're going to substitute 2 in for a in this definition. So we'll write our definition, and we've got f of x minus f of 2 over x minus 2, and we'd like to reach a point where we can substitute in 2 for x. Well, we have to first put in our function, so instead of f of x, we'll have x squared, because that's our function. And instead of f of 2, we'll have 2 squared. And resist the urge to simplify every time, because what I'm going to look at here is I see the difference in 2 squares, and that would nicely give me something to cancel out here. So I'm going to write x squared minus 2 squared as x minus 2 times x plus 2. Then I can cancel this quantity out, this factor out, in the numerator and denominator, and get 2 x plus 2. So now I've got f prime of 2 equals the limit as x approaches 2 of x plus 2, which is going to be just put in a 2 here, and we get 4. So that tells me that the slope of f of x equals x squared at 2 is 4. So if f of x equals x squared, then f prime of x equals 2x. We learned that in the last example. So that tells us then f prime of 2 times 2 is 4, and we just proved it with our alternate definition. I'd like to quickly show you one more example using the alternate definition, because you don't do the same thing to every one. The goal is to just not have 0 in the denominator so you can simplify. So this time we're going to find dy dx. Remember, that's just another way to say the derivative or the slope at x equals 4. When f of x equals, now we're going to use the square root of that. So we always write our definition, and remember this is the limit as x approaches 4, of f of x minus f of 4 over x minus 4. Well, my function is square root of x. So I'm going to write it down again as the square root of x minus the square root of 4 over x minus 4, and it's the limit as x approaches 4. I need to get x minus 4 out of the denominator, so I'm going to use the conjugate method. I'll multiply the numerator and denominator by square root of x plus square root of 4. What that's going to do for me is x square root of x times square root of x. Square root of x squared is x. This positive and this negative product are going to cancel each other out, and then I've got square root of 4 squared, which is x minus 4. That's nice, because now I can cancel that out of the numerator and denominator and be left with 1 over square root of x plus 4. That's what's left, plus, the square root of 4. And that's going to give me 1 over 2 plus 2, which is going to give me 1/4. So that tells me that at x equals 4, my slope of square root of x function is 1/4. It's rising 1 for every 4 it runs. Now, let's take a look for a minute at the graphical relationship. Okay? If we have a graph of f, we can calculate slopes between points on the graph, plot the points on another axis, and see the graph of f prime of x. Let's take a quick look at how we do that. Consider f of x equals x squared. We've been using this right along. And you can put key points in at -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Well, that gives me this table, and it's kind of nice because tables and graphs, you might get one or the other, so let's be able to use them both. Between -3 and -2, if I were to think about the slope of this secant line, my point would be negative 2.5, so you want to find the midpoint between your x-coordinates. And then use the slope formula with these 2 points to find the slope of the line, 9 minus 4 over negative 3 minus negative 2. Get negative 5 for the derivative, the slope at this point. I can do the same thing between negative 2 and negative 1. That'd be the point negative 1.5 for x. And when I calculate the slope, 4 minus 1 over negative 2 minus negative 1, I get negative 3. And I can work through this entire table that way. And what I'll be getting is an input, an x and a y value for the derivative graph. So I can plot negative 2.5, negative 5, negative 1.5, and negative 3, negative 1/2 and negative 1, 1 and positive 1/2, 1.5 and 3, and 3 and 5. And when you connect those, you see that we found the graph f prime of x equals 2x, which we've already calculated analytically to be the derivative of x squared. Also, we can work backwards. If we know the graph of f prime and have some clues, we can find the graph of f of x. Let's say we're given this scenario. We know f of 0 is 0. We've got this graph over here, which is the graph of f prime, and it's telling us slopes. And we know f is continuous for all x. So I know f prime isn't defined at x equals 1 because I've got these open circles. So, and f is continuous, so I know I don't have a jump there, but I could have a corner or a cusp. So I'm looking into that. I also know that the slope for all the x values less than 1 is negative 1, and the slope for all the x values greater than 1 is 2. So I can make a graph here, and I can start it at f of 0 is 0 because I was given that as a clue. And I know that from 0 to 1, my slope is negative 1. So I'm going to go down 1 to the right 1 and get that point. I can also continue this line with a slope of negative 1 by going up and to the left. And I've got this half of my graph of f of x. Well, I know my slope is 2 for all x greater than 1, so from 1 I'm going to go up 2 to the right 1, up 2 to the right 1, and I could continue this indefinitely. So right here, because I had the graph of f prime telling me the slopes of f, and I had some clues. I knew where to start this graph, and I knew it was continuous, so I knew I didn't have a jump anywhere between at x equals 1. So that's a way you can create these graphs, and I'm sure you can do that. So you'll see an example in your textbook. How do we graph d dx of f of x giving data? Please go ahead and just calculate those slopes. You're going to calculate midpoint, and you're going to calculate slopes of these four, and you'll just continue doing that right on through. And technology will get you there following these steps, which I'm just going to put on the screen for a minute. You're going to have to pause and play them because I'm running out of time. And now finally, one last thing, one-sided derivative. Your function is going to be differentiable if it's differentiable everywhere on a closed interval, and the limit from the left has to equal the limit from the right. So if we look at a piecewise function, you think first you have to ask yourself two questions. Is the function continuous? And is the function differentiable? And is the derivative the same from the left and the right? So to check continuity, we do it just like we did in Chapter 1 and 2. We just take this point, we plug it in here, we plug it in here. If it's the same y value, we know it's continuous. So that's all good. But then to check differentiability, is the limit from the right equal to the limit from the left of 0? And in this case, we know that the limit as h approaches 0 of x squared, we know that's going to be 2x. So if you put in 0 there, it equals 0. We didn't really look at the limit of 2x, and that's going to give us this. You're going to get 2. Limits are not the same. Limit will it's not differentiable at that point. You can find a corner or a cusp there. And I hope this is helpful, and we'll see how it goes.